Hello, everyone. Goedenavond, good evening. Welcome to our webinar. This is KNVTS Amsterdam 5th webinar. My name is Mariana Candela. I'll be your host for the evening. I'm a mooring and subsea engineer, and I'm also a board member of KNVTS Amsterdam. KNVTS is the Royal Dutch Association of Engineers in the Maritime Industry. Tonight, we will have a wonderful lecture by Roger Basu on the evolution of offshore structures, the transition from oil and gas to wind with a focus on the US market. Roger is an experienced structural engineer, having worked at ABS in Houston and a naval architecture firm in Ottawa, Canada. After retiring for ABS, Roger taught at Webster Institute in Long Island and now runs his own company, Roger Basu and Associates Incorporated, based in Toronto. Welcome, Roger. Hi, welcome, Roger.
Thank you.
We will have now a session of 45 minutes, more or less, and then we can have questions for about 15 minutes. Please type your questions in the chat box as you think of them, and we will try to answer as much as we can at the end. Enjoy the lecture.
All right. Thank you. Thank you. Thank you for the introduction. Let me see if I can get all this working. So I think you should be able to see my screen right now. Can I get an indication that that's the case? I just want to make sure before I start that people can see my screen.
Yes, we are all seeing your screen.
Oh, excellent. Okay. Well, good evening, everyone, or good afternoon, depending on where you are. Thanks very much to the Amsterdam branch of KNVTS for inviting me to speak. I'm going to talk about offshore structures, or the evolution of offshore structures from oil and gas to wind. I'm a structural engineer by training. I've worked on structures all my life, basically, mostly on ship and offshore structures, but I also have some experience on land-based structures, but that was much earlier in my career. I do have some background also in wind effects on structures, so I know a bit about the wind. I worked for 5 years I did some research at a wind tunnel laboratory, so I have some background in wind. I have not worked directly in offshore wind, but I take a great interest in the subject. And it's kind of exciting to see this transition that's occurring, because I've experienced these transitions in the past, but this is a very exciting one. So I've kept in touch with what's happening in the industry, and here are my thoughts. I'm going to focus on the US simply because that's my main experience, and that's where the big changes are coming right now. Okay. So a quick overview, it's really two presentations rolled into one. The first half is going to be on oil and gas offshore structures, a very quick run through the evolution of these kinds of structures, again, focusing mainly on the US. And then I'll move on to offshore wind structures. There has not been a lot of work in this area in the US, but there's every reason to believe that's going to expand very rapidly. So for oil and gas offshore structures, I'm going to talk about the basic evolution, talk about production platforms. Those are the ones that are there for many years, 20 years, 30 years typically. And then a little bit about drilling platforms. These are the platforms that before you actually go into production, you have to find the oil, drill exploratory wells and that kind of thing. And then just a couple of words about selecting the right concept. Then I'll move on to offshore wind structures. And this is going to be a more general discussion because we're in the early stages of offshore wind structures in the US. Okay, so when did the first structures appear in the US? Of course, they were on land quite early on in the 19th century, but it was late in the 19th century where we started to see oil and gas installations on the coast. And the picture on the right shows just such an installation. This is off the coast of California. So basically, they extended piers out into the sea with derricks, pumping the oil and so on. And some of these were operated for about 25 years. There were other similar sorts of installations in lakes in the States, Louisiana, Ohio, Lake Erie. But at the same time, I think the Caspian Sea actually started earlier. In fact, they're still producing oil. And Lake Maracaibo in Venezuela, the same story. Fairly shallow waters, but the same sort of experience, but mostly shallow waters. So in the late 1930s, the focus shifted to the Gulf of Mexico, and that still is the main offshore oil producing area in the US. And you saw this sort of steady evolution of taller and taller structures. 1947 is often used as the starting date for these. In fairly shallow water there, in six meters of water. And eventually, as they moved into deeper and deeper water, you got up to around 100 meters of water in 1967. So at this point, other parts of the world were opening up in a big way as well. There were already installations in the Persian Gulf off the coast of Malaysia, Indonesia, and so on. All fairly shallow waters, though. It's the interest in deep water, I think, I would say, started in the North Sea, and this is the first time I got involved. The picture on the right is a structure that I worked on. It was the Thistle Alpha platform installed in 1976 in 162 meters of water. And basically, what a lot of the initial work was done by US engineers. They adapted their Gulf of Mexico type designs for the North Sea. The big difference was the climate was pretty severe in the North Sea compared to the Gulf of Mexico, if you exclude hurricanes. But I remember the design wave height that we used in designing structures like the show on the right. We were using 30-meter height. I mean, this is quite a massive design wave, but it sort of reflected the severity of the North Sea, the North Sea climate. This is my experience, but at the same time, there were other sort of more innovative structures also going into the North Sea, especially in the Norwegian sector, where they started to use concrete in a big way. And many of you will know about these structures. Many of them are still there, the Condeep platforms and so on. But I won't talk about those too much. So the focus is in America. So what started to happen is that the search for oil moved into deeper waters. And as we know as engineers, when structures get taller and longer, they tend to get more flexible and you get lower and lower natural frequencies. But we all know we need to avoid resonance. So this is a very sort of simple graphic of it depicts energy as a function of frequency for waves and for wind. So you see in this picture, waves have frequencies of the order of 0.1 hertz or a period of 10 seconds or so. And the typical structures, tall platforms of the kind that I just showed you, had periods of the order of 3 to 4 seconds. So you're well away from the energy-bearing frequencies of the waves. But the danger is, the taller you make these structures, you start to attract the resonant conditions from waves. And also the other thing is that the costs go up quite rapidly. All right, so what did engineers do? They said, all right, we can't make them taller and have the same sorts of stiffnesses. What if we make them deliberately much more flexible and avoid waves altogether? So you got this class of compliant structures that were built. Some of them are still operating, even in the Gulf of Mexico, And there certainly used to be some of these off the coast of California. I don't know if they still exist, but I know the Gulf of Mexico ones do. And they avoided that wave problem entirely by making extremely soft structures. So the periods of these were of the order of 30 seconds. So it's hard to imagine, but if you were on top of one of these structures, it would move back and forth, and it would take half a minute to do that. Quite gentle movements, but nevertheless, the deflections were quite significant. I can't remember the numbers offhand. And we got up to depths of 530 meters of water, so quite deep for a fixed structure. But this is the limit. So if you make them even bigger, then you start to attract forcing from the wind, because the wind has energy in the kinds of frequencies that we're talking about. All right, so then we had to move to floating production platforms, and there's a variety of different kinds of these structures. Unlike the fixed structures, at least the ones in the North America, the steel ones, which were all frame construction, you had a variety of different kinds when it comes to floating. So just looking very quickly at the kinds of structures that were out there, starting with the compliant one on the left that I talked about. So that was the last of the very tall fixed structures. We started to move towards the newer concepts. One of the first ones was the TLP, the tension leg platform. A couple of bits of that. The next is, they've called it a semi-FPU here, but we're more familiar with it as a semi-submersible. And I'll postpone a discussion of that till later, because that's a kind of a special case. Actually, these existed before TLP, so they've been around a long time. But I think it's kind of a special structure. The next new variant was the spar structure. Several kinds, several configurations. And then we started, actually, there's a lot of overlap between all of these TLPs, spars, FPSOs. So what's shown here is a ship-shaped FPSO. I'll talk more about each of these in a minute. Left to that is another FPSO, but that's an unusual one. It's circular, and that's also been used. So it's not ship-shaped, it's a circular shape. It has a circular-shaped hull. And the last one I'd like to spend a few minutes on is the FLNG. That's kind of like an FPSO, but much more sophisticated. All right, if we look at each of these a little more closely, the TLP was first installed in 1984 in fairly shallow waters. This is the kind of water that you could easily put a fixed structure. I wonder if it was a kind of an experiment, if you like. And it went in the North Sea, not the Gulf of Mexico. And then about 30 of these have been installed in various places, but almost all of them in the Gulf of Mexico. And it's Chevron's Bigfoot TLP that holds a record in terms of water depth, about almost 1,600 meters of water. And then if you move to the spars, the deep draft spar, this is a concept developed by an engineer called Ed Horton. I was in Houston later after that period, but there were a lot of stories going around in the industry. And one of them was that Ed Horton developed this in Houston in his swimming pool. And they were using, him and his colleagues were using empty beer cans and Coca-Cola cans and doing experiments. It's probably true because I heard it from very reliable sources. Anyway, getting back to the spar, 3 different configurations were developed: the classic spar, truss spar, and the cell spar. Now, the classic one is the first design that you see on the left, basically a big tube. And you'll see those strakes around it. That's to stop vortex-induced motions. It's a thing that you do worry about in the Gulf of Mexico. In certain parts of the Gulf of Mexico, we have loop currents. The currents are quite high. So there was a danger that vortex-induced motions would cause quite severe motions of these installations. And the idea of the strake is to break up that the coherence of that process of vortex shedding. So the next one is the truss spar, partly to address the vortex-induced vibrations problem, but also solves other problems. I guess it's a little lighter. Truss construction is usually the lightest you can make. I know the bottom plate was there for a specific reason. It's called a heave plate. It tried to minimize the heaving of the structure. And the last one is the cell spar. I think only one of these was ever built. And it's basically replacing one large tube by a number of small tubes. And that was more from the construction point of view. It could be built in lots of different yards, whereas these ones based on large tubes could only be built in a few yards. So that's the origins of the spar. The first production first production platform saw service in 1997. The Neptune, I think it still operates in the Gulf of Mexico, 588 meters of water. There are about 21 installed, most of them in the Gulf of Mexico, just 2 in other areas. And now you're getting really deep waters now. Perdido is in the Gulf of Mexico, almost 2,400 meters of water. These spars tend to be heavier than equivalent semis and TLPs. Okay, going back to the semi-submersible, I said I would return to this. So these are quite interesting. They have an interesting history. They actually started as submersibles. So it's basically that kind of configuration would be towed to site, and then they would ballast the pontoons. It would sit on the seabed, and they would do whatever they needed to do, usually exploratory wells, drilling exploratory wells, and the like. But one thing they did notice that in transit, when they were moving these units, the motion characteristics were unexpectedly good. And that was mainly because the pontoons were below quite a lot below the surface of the sea. So the wave motion wasn't having as a bigger effect as it would if it was on the surface. So it evolved from that. So they've been around a long time. It's the second most popular floating production system. You'll see them in many parts of the world. Brazil, North Sea, Gulf of Mexico, they all have large numbers of semi-submersibles doing production work. The deepest water, again in the Gulf of Mexico, is the Independence Hub, still operating. The semi-submersible is really versatile. It can be used in a range of water depths. It's similar to the FPSO in that regard. It has good platform area. It's just the nature of it. It's unlike the spar, which your whole processing plant is over one tube. You can spread it out. In the case of the semi-submersible, you've got 4 legs, and you can put them fairly far apart, so you have a nice area to work with. And it also has reasonably good motion characteristics. Now, the FPSO is the most popular floating production system. It's basically a ship-shaped structure. The hull is used for storage, and it supports the plant on top. It's quite crowded. Most are based on converted tankers. So tankers that have maybe got another 5, 10, 20 years life will be converted for oil and gas extraction purposes. Very attractive in places where you don't have a lot of infrastructure in terms of pipelines and so on. So you have to store the oil, at least temporarily, and a shuttle tanker would come and remove the oil. So in concept, that's quite similar to the FLNG. The same sort of thing, but this has an added sophistication. It not only extracts the fluid from the seabed, but it also processes it and turns it into liquefied natural gas. And hence, if you look closely at this one, this is the Prelude off the coast of Australia. It's very, very compact. It's got a lot of equipment on board the vessel. It makes it kind of large, almost 500 meters long, as you can see from the numbers down there. And alongside, you see an LNG carrier. This is a shuttle carrier. So every so often it'll come along and take off the LNG and move away, and then come back a week later or whatever the cycle is. So that's the last of the floating production that I wanted to talk about. I've got a few words about concept selection. I'm not going to talk about this slide because it's outside my area of expertise, but I thought it was important to make people aware that it's not just technical issues that decide the concept selection. It's very important, of course, but there are a whole host of other issues that you have to worry about: commercial schedule, which yards have capacity, and so on. So there's that has to be borne in mind. But focusing on the technical side of things, concept selection. This is a graph that we've seen a similar form of this before. Again, you're trying to avoid motion characteristics that match the energy bearing frequencies of the waves. So you can either make them very stiff or very soft. So to try and avoid that peak. And so on the left-hand side, TLP, it's quite stiff because it's held down by attentioned tendons. So it has a high natural frequency or a low period. And then on the right-hand side, we've got these installations that are supported by catenary moorings and things like that, which are much softer. And so they have periods that are quite a lot bigger than where the energy is in the waves. Okay, I just wanted to, I'm not going to go through this table in any detail, but these are the sorts of things that technical people worry about when they are trying to decide on which configuration suits them the best. So there's the issues, a lot of the choices are made by the water depth. What water depth are you going to be working in? And also the motion characteristics of the vessel, because that has an impact on a number of things. For example, under functionality, it talks about dry and wet trees. That's the sort of equipment that interfaces between the well and the installation. If there's a lot of movement in your structure, like a semi-submersible or an FPSO, you tend to put these on the seabed. If you can, you put them on the installation, as you often do with spars and TLPs, because that equipment is easier to get to, easy to maintain and repair, and so on. Water depth is another major consideration. So things like spars and TLPs are better for deeper waters, and that goes to the previous graphic that I showed, where the frequencies matter. Semi-submersibles and FPSOs are much more flexible in that regard. They work in any kind of water depth, any reasonable water depth. Okay, payloads. Again, this is fairly obvious that the spar has some limitations. The others don't have any real limitations, but the spar does, because it's basically you're supporting the whole installation on one big tube. So the platform area can't be that big. Hence, they tend to be on several levels. Riser types, that's again associated with movement. If you're more restricted if you've got installations that can move around a bit. So you have to use steel catenary risers in that case, but you have more flexibility when you using platforms that are stiff and don't move around as much. And the last two categories are to do with installing and decommissioning and commissioning and all the rest of it. And the easiest ones to talk about are semi-submersibles and FPSOs. You just get towed to site, you put down some moorings, and I'm oversimplifying, I know, but it's relatively simple with a semi-submersible or an FPSO. TLPs and spars are much more difficult to deal with, especially the spar, because these are they usually go out floating on their side and then are upended, and then the moorings are added. So decommissioning something like that is much more involved than an FPSO, which is basically a ship and can be towed away relatively easily. Okay, just a couple of words about drilling platforms, because it's kind of relevant to some of the stuff we talk about later on, right at the end of the presentation, actually. I've already talked a bit about semi-submersibles and submersibles, so I won't dwell on that. But these are units that you need typically for a short period of time, not for 20 or 30 years, but for several months while you're drilling exploratory wells. And you do, if the field turns out to be interesting to the operators, they'll also want some production wells to be drilled. They'll be capped and they'll be moved off, and then a production system will come and that will be installed. So again, water depth is the important determinant of which one you use. If it's relatively shallow, up to about 150 meters, jackups are a very attractive option. They move around like a ship. The hull acts as a that's the flotation that comes from the hull. They can be towed like that with the legs up in the air, basically. And then when it gets to site, the legs are jacked down and you get a nice sort of firm foundation to do your drilling. If it's deeper than that, you use things like semi-submersibles and drill ships. So they're, as we've discussed before, these are quite flexible units in terms of water depth. You can have them in shallow waters. In that case, you use moorings typically. If you're in deeper waters, it's usually done by dynamic positioning. So you have thrusters that keep it in place. It's kind of expensive because you use a lot of fuel when you're trying to keep it positioned, especially if there's big currents and waves around. Okay, so that's a quick survey of fixed and floating offshore structures. So I think I can move to offshore wind. The focus here is going to be a bit different. I'm going to go back earlier. We are just in the beginning stages, at least in the US. So I wanted to sort of set the scene. So the first graphic I'd like to start with is the transition that's happening in the US. And this will give you a very good idea. Actually, this kind of surprised me, and I suspect a lot of people will be surprised by this. So, they use coal here, oil, gas, all the fossil fuels are used quite extensively here. So when I ran across this graphic, and this comes from the US government, so I assume it's reasonably accurate of what's going to happen. This shows the new energy that's going to be added, new sources of energy that's going to be added in the US in this year, in 2021. And you can see it's dominated by renewable energies. 70% of the new energy will be from renewables. You've got solar is the dominant one, and wind is a close second. And there are other ones as well, but they're much smaller. Natural gas is here as a significant amount, because some people regard it as a sort of a transitional fuel, going from the fully fossil fueled energy to renewable energy. So you will see quite a lot of use of natural gas. But this surprised me that this was 70%. All this wind is on land. A very, very small proportion is offshore winds. It's about 0.1%. So it's not a lot, but I think that's going to change. And so we start to see the parallels already with the oil and gas development. We started on land, we moved to shallow water, and then to deep water. So the wind is following exactly the same trajectory. Offshore is currently quite small as a percentage of global electricity supply. I've got this number back from 2018. I expect it's a little bigger now, but 0.3%, not a lot. But it's expected to grow rapidly, and we'll talk a bit about that later on. And there's several reasons for it. It's clean, obviously. We are in this sort of transition to greener sources of fuel, but there are also other reasons. All right, so let's start with land. That's how I started off talking about oil and gas. Same thing with onshore wind. There's just one slide on this subject. Just wanted to identify the advantages of onshore wind. It's usually located on land of minimal value, and this is attractive in places where you have a lot of land. You have low population densities. The infrastructure needs are small. The installation and maintenance is easier, but I say up to a certain size. And you can see on the photograph on the bottom what happens when you've got a big turbine blade to move. I don't know how long that is, maybe 60, 70 meters. So when you get up to 110, 115, that's the kind of numbers we're talking about nowadays. It becomes a huge logistical challenge to move these kinds of components around. But it does have this advantage that it's less costly. The infrastructure is less costly. You don't need a boat to to get to the site. Advantages of offshore wind, better wind characteristics. I'm going to focus on that because that's an area that I understand better than all these other ones, which are much more difficult to deal with. Less interference with other human activity, less noise, less visual pollution. But if you read the sort of recent history of the developments of offshore wind in the US, there's still quite a few objections that you get from the fishing and boating community. And depending on where the turbines are, how close they are to a shoreline, people don't like the look of them if they're too close. The other advantage of offshore is that it's far from habitation but close to markets, and I'll show you what I mean by that in the next slide or two. All right, so I said I'd say a few words about why wind is better over sea than over land. The graphic on the right will give you some idea of the advantage. This shows the mean wind profile. And on the left-hand side, this is the typical wind profile that you see over rough terrain. Rough terrain, I mean cities, towns, that sort of thing. And then if you've got smoother terrain, like let's say a forest or fields and things like that, out in the open, the mean wind profile looks like this. And then finally, when you get out to sea where it's the smoothest possible surface, the profile looks like that. So you see at a given height, wind speed is quite a lot higher if you go offshore. I've put a graphic there showing, I think that's based on an 8 megawatt wind, offshore 8 megawatt wind turbine. At hub height, you can see this might be, I don't know, 5 meters per second. This will be about 7 meters a second. But once you're out at sea, you're talking about, let's say, 9 meters a second. And remember that energy is proportional to the cube, the wind speed cubed. So you get a lot of benefit from higher wind speeds. The other thing is the winds are steadier. There's less thermal effects over on sea, so it's less turbulence. So that has some advantages. Okay, so once we've got the wind characterized, then we are ready to do some design. I've got a few slides just summarizing the design issues and as a lead into the issues that I see in the US. So in addition to waves and currents, you need a more advanced treatment of wind than you're used to. If you're working on offshore oil and gas structures, winds are important, are very important, but you don't need to characterize it in the detail that you do for offshore wind turbines. Wind turbines, especially when they get large, you then have to take account of the fact that wind is not a steady load. It fluctuates, as I show in the graphic at the top. That's a typical wind trace. It varies not only in time, but also space. Spatially, across the width of the structure, what it sees at one end is different to what it sees at another end. The sort of thing that designers of suspension bridges worry about, because you can get them up to, I don't know what the numbers are now, but typically 2,000 meters apart, one end to the other. So what's being experienced at one end is quite different to what's being experienced at the other end. So once you get these very large wind turbines, 15 megawatts and above, you're going to have to worry about these sorts of things. The other thing that it's less of an issue, but sometimes is important, because I've already seen people mention this in papers and so on, is wind veering. This is not an issue if you're close to the ground, but if you start to move up into 100, 200 meters, wind veering might be an issue. And wind veering is the change of direction of wind as you go upwards, okay? So that might be significant for something like a wind turbine. The other thing is the atmospheric stability has an influence. Again, this may probably be more an issue on land than sea, but it could be an issue. So over land, typically at night, the airflow tends to be stable, so it's quite steady. You don't see the sorts of fluctuations that I show there. And then in the day, it's the opposite, especially when the sun is shining. Okay, so now that once you've defined your environment, then you're ready to start to think about doing an analysis. And this gives you a sense of how complex the whole process can be. On the left-hand side, we've defined the external conditions, that is the wind flow and waves and currents, which are particularly important if you've got a floating installation. And then if I take the wind, apply aerodynamics, I can get some aerodynamic loads on the whole system, and the same with the hydrodynamics, though that tends to affect mostly the platform itself. But it can affect all the parts of the installation above the sea level. But you can see that it's an entirely highly dynamic system. So you have to have pretty good models, dynamic models of the wind and the waves and the current, because they all play a role in the response of the system. Okay, so looking at the kinds of foundations these lines have, I've just put three or four out there. There are others. So these are the typical fixed base concepts. And then when you look at floating concepts, you'll see some of the same sort of terminology that was used in the oil and gas floating structures is used here. Of course, they're already talking about different concepts that are unique to offshore wind. And that's exactly what you expect to see. And that's what happened with the offshore oil and gas. You started with structures that were basically adapted from the land, but then you started to develop unique configurations that were more suited to the sea. Okay, so we've talked about fixed bases and floating bases. What's actually happening? This is slightly out of date, 2019, but it will give you some idea. It's dominated by fixed base. The world offshore wind turbines are almost all fixed base. And within that, it's the monopile that dominates. This is showing the installations in terms of megawatts of power, what kind of foundation the installation has. So monopiles is more than fixed base and floating put together. There's hardly any as a percentage of floating installations, but more are coming, as we know, some big ones off the coast of Scotland. And was it in Spain, I believe, or Portugal? I can't remember where, but there's a new one recently announced. So for the time being, fixed base is what we're looking at. Okay, some of the challenges that are unique to the US context, hurricanes and earthquakes. Now, I don't believe there's a lot of experience with offshore wind farms in these kinds of regions. And this is what we have to contend with offshore, US offshore. So hurricanes, the East Coast, and that's where most of the focus is right now, is a hurricane-prone region. And some people argue that you're going to see more and more of those in the future, and they might even become more intense. So it's a mixed wind climate. Not only do we have these hurricanes, but we have normal storms, if I can call it that. So both are significant on the east coast of the US. And then once we move to the west coast, then of course that's a very strong seismic zone. So you have to worry about the effect of earthquakes on your structures. Okay, so there's three issues I'd like to raise as to the reasons why the focus right now is on the east coast of the US. The first is population. So this graph shows all the towns and cities that have a population greater than 1,000. This is just one way of showing population density. So you can see that the population is quite dense on the east coast, especially the northeast, but all right down to Florida and in the Gulf of Mexico and Texas and Alabama and all these places, all heavily populated. People like to live on near the coast. The same on the west coast. So it makes sense to have wind farms, close by to where your consumers are. So that's one thing, population density. The other thing is wind resources. And this is a plot of annual average wind speed at a height of 100 meters. So that's the sort of region that we're interested in for offshore wind farms, at least right now, maybe bigger later on. And you can see, of course, the darker the blue, the more intense the wind. And of course, the coastal areas see more wind for reasons that we've already discussed. On the west coast, the east coast, less so in the Gulf of Mexico, but certainly the northeast and the west have got very strong winds. So that's another reason why it's attractive to put your offshore installations in the sea. Okay, the last point I'd like to make is that a continental shelf. If you look at the blue region, that is water depths of 0 to 30 and 30 to 60. And 60 seems to be the sort of general cutoff point for fixed and floating offshore installations. And you can see that on the East Coast and the Gulf of Mexico, it's pretty shallow for quite a distance. So as I remind you, sort of dark blue is still less than 60 meters in depth. If you go to the West Coast, it's a different story. There's hardly any continental shelf. It goes out for a short bit and then dips down very rapidly. So you're talking about installations, if they go there, will be in more than 60 meters of water. And that also applies to Hawaii, which is another area of interest for offshore wind farms. So those are the three reasons that East Coast is very attractive. One is the population. Two is the wind speed that I showed you, and then the large continental shelf. Okay, now this is something that I was not going to talk about, but after listening to people who know more about the subject than I do, they say this is a bit of an issue. When the European operators come to North America, their experience is quite different to what they're accustomed to in Europe in terms of getting permissions and so on. So just a little bit of history. All offshore energy development, whether it be oil and gas or wind, is regulated by at the highest level by these two agencies. They're both part of the Department of Environment. You have BSEE, Bureau of Safety Environmental Enforcement, or BSEE, sometimes it's called BSEE, BOEM, Bureau of Ocean Energy Management. And so these two organizations regulate and look after offshore development since 2011. Before that, it was a single organization that had both functions in one. And that was changed after some of you will remember the Deepwater Horizon accident in 2010, which resulted in a huge oil spill in the Gulf of Mexico. And it was decided after that to split the function into two. So as far as offshore wind is concerned, you're going to hear much more about these because we're in the early stages. Later on, when the installations are running, the BSEE will get more involved. So the BOEM process for developing offshore wind farms has 4 stages. They do the initial work like the planning and analysis. This is before any operators or investors get involved. They look at the areas of the ocean that's part of the outer continental shelf to find areas that are good from the environmental point of view and the engineering point of view. And at some point, once they've completed that, they go into the leasing, and then they'll invite bids from operators. And then at this point, most of the work is done by operators. They do a site assessment. They'll put up mid-ocean towers to get a sense of what the wind and wave climate is in a certain area. And then later on, once they produce what's called a site assessment plan, which is submitted to BOEM. Once that's approved, they go to the next stage and develop a construction and operations plan, which then has to be approved. And at that point, they're ready to go. This whole process can take 10 years. So this is one observation you hear. There are a number of other important regulations that are administered by BOEM, mostly associated with environmental issues, Endangered Species Act, Migratory Bird Treaty, and so on. The one that you will keep hearing about is the first one, the National Environmental Policy Act, NEPA. That sort of drives a lot of the work that BOEM does, and also the operator will have to do in getting permission to build an offshore wind farm. The one that I've underlined is a bit different. It's not directly to do with the offshore wind farm itself. It's to do with ships that provide support to the wind farms. This is commonly known as the Jones Act, but the official title is Merchant Marine Act of 1920. And this governs how the ships are built and operated in the US. And I'll talk about that in the next slide. So the observation that I've heard, I don't have direct experience of this, but people have said, more than one person has said, the US permitting process is quite complex and lengthy. You have to deal with at least 3 levels of government: the local level, state, and then federal agencies. So there's quite a lot of interaction with government agencies. And these apparently have a challenge on how easy it is to get money to go ahead with your project. Okay, the Jones Act. Just to the basic requirement is that a ship traveling carrying goods from one US port to another US port has a number of restrictions. It's got to be 75% US owned. It's got to be built in the US. Crewed, minimum 75% of US citizens, and the ship has to be registered in the US. It has to be a US flag. Of course, there's pros and cons. From the US point of view, it maintains a marine industry. You maintain a maritime workforce. So these are regarded as advantages. The main downside from the point of view of offshore wind farms is the expense that you have to go through to build a ship to provide, wind turbine installation vessels, supply vessels, that kind of thing. And this was only settled as an issue last month, or maybe in December, I believe, where they said offshore wind farm work is covered by the Jones Act. Okay, so I'll talk a bit about the projects that are underway right now. This chart is out of date. It's 2 years out of date, but I just wanted to show this to give you an idea of where the action is. So this summarizes where offshore wind farms are under development at various stages of development, starting with planning right through to operating. And you'll see that except for 2 exceptions, they're all on the East Coast. And the exceptions are Hawaii and California. But these are much earlier development. They belong in the planning stages. You've got to go through all these other ones, these permitting and financing and so on, before that becomes a reality. So for the foreseeable future, we're going to see all the development on the East Coast, with one exception, which I'll talk about later. Okay, that I almost forgot to mention that. There is one unit that is operating. So it's so small that in terms of megawatts, 30 megawatts, you can hardly see it. Okay, so this is the current state. Maybe slightly out of date. I picked this off the BOEM website maybe 3-4 weeks ago. So it might be slightly out of date, but it lists all the projects that are under consideration right now. To get an idea of what status, where they are in the development process, if you look at the last column, you'll see SAP, COP. I've mentioned these before. So the SAP is the site assessment plan, and COP is the construction and operation plan. And so it's the COP ones that are more imminent. They're close to becoming operational. I've highlighted 3 of them because those are the ones that I'm going to talk about. But I'm going to start by talking about one that's not on that list, because this is the only operational wind farm right now in the US. This is an Ørsted project that started back in 2016, a small farm, 30 megawatts. It recently had some problems with the undersea cable. They had to relay some of it. And that's actually been completed only just last month, so it will restart again. So it illustrates, once they lost this power, they went back on diesel generators. So this island, Block Island, gets its power from diesel generators until we got the wind farms. Okay, so the next one is the South Fork offshore wind farm, Ørsted and Eversource. Eversource is a utility company, so they've gone into partnership. This is going to be built off the coast of Rhode Island and Massachusetts. Even though it's regarded as a Rhode Island, Massachusetts project, and that's simply because the farm itself is off their coast. All the power goes to New York. It'll travel westwards and make landfall in Long Island. They haven't defined exactly the configuration, but they're saying that there won't be more than 15 turbines, and the maximum output will be 132 megawatts. This is supposed to be operational by the end of 2023. Vineyard project, this has got the go-ahead, I believe. It did stop temporarily. Much bigger development, jointly by Avangrid and Copenhagen infrastructure partners, 800 megawatts, almost getting up to 1 gigawatt. 15 miles off the coast of Martha's Vineyard, that's this island here. That's Cape Cod, Massachusetts. So as I said, they decided in the middle of getting the permissions from BOEM, decided to change their wind turbine model, and that delayed things. But that it seems to be back on track. And again, will be operational by 2023. Some New York projects. I mentioned this for a number of reasons. Three basic reasons. One is these are two big new wind farms. The project has already been awarded to Equinor, who is partnering with BP. Both well over 1 gigawatt each. So quite an extensive project. There was an earlier Empire One was awarded earlier. So this is interesting in itself. But what I really wanted to focus in on was New York has decided to invest heavily in wind, not just in terms of wind farms, but also in developing an infrastructure which will serve not only the New York market, but also the other wind farms that I've talked a bit about. So we need infrastructure, obviously, to support operations, maintenance, manufacturing, and all the rest of it. And the idea is to convert some of these ports into facilities to support wind farm operations. Some of these ports don't see as much business as they used to, so the idea is to convert 2 of them. And there's even talk of involving ports along the Hudson River. Of course, these would have to be pretty modest in size, but it just gives you an idea where the focus is. These 2 I think are somewhere just on the the west end of Long Island. And the New York agency that's leading this is NYSERDA, New York State Energy Research and Development Authority. The other thing NYSERDA is involved in is training, because they realize they need people as well. It's not just getting wind farms up and running and providing the supporting infrastructure, but you need people as well. So they're investing in a training institute. They're putting in $20 million, and they're using the SUNY system, State University of New York, which is quite a big university system with several campuses. And the initial goal is to train 2,500 people to support offshore wind projects. There's another similar sort of initiative called the National Offshore Wind Training Center. That's going to be in Long Island, New York. It's a joint Ørsted Eversource project. Eversource is another one of these utilities, and they're working through an outfit called the Workforce Development Institute in New York. Same sorts of objective as the Offshore Wind Training Institute. Okay, the last project I'd like to talk about is not on the East Coast. It's the only one that I know about that's in the Great Lakes, and this is just north of Cleveland in Lake Erie. A joint project again, Lake Erie Energy Development Corporation with Fred Olson Renewables. And you can see how long they've been talking about this project since 2009. It's only just got approved last year in May. And when it got approved, I remember there was quite a uproar because they said, oh, yes, you can go ahead. Everything is agreed to. Oh, the only limitation is that you can't run the wind turbines at night, so which makes it unfeasible. Anyway, they seem to have sorted that out, and now it's going to run 24/7. Construction starts in next year and should be operational by the end of next year. So those are the projects that I just wanted to give. It gives you a flavor of what's happening in the east coast of the US, except for that, and also the Great Lakes. So ships for offshore wind projects, this is important for a number of reasons, but the main one is some heavy investments are being made, which means that the people who are making the investment are highly confident that all these projects will go ahead, even though they've been slow to start. They expect rapid expansion in the coming years. So just some examples of the ships that have been recently ordered. We call them first Jones Act service operational vessel. The other important point here is that it'll be operated by Edison West Offshore. And this is another example of what's happening, the sort of move from the oil and gas to offshore. Edison West has been operating for decades in the Gulf of Mexico, supporting the oil and gas industry. And now it's moving into offshore wind. The intention is that it will support 3 different wind farms. It's classed by the American Bureau of Shipping, my old employer. And this was all construction award was made fairly recently. It's a vessel, a wind turbine installation vessel, quite a big one, designed by Gusto, under construction in Keppel in Texas, near the Mexican border. As I say, a big one, 143 meters long, 56 wide, one of the biggest WTIVs that is planned. I think that's all I had to say. That's a quick overview of the offshore field and oil and gas field. It looks like it's really taking off now in North America, and we expect to see some exciting developments. Just a few concluding remarks. The search of oil and gas transition from land to offshore, first shallow waters, then to deeper waters. And at the same time, you went for fixed space structures to floating systems. Several engineering innovations, the design of all those, development of all those concepts that I talked about, the SPA, for example, semi-submersibles, all came from innovations as they moved into deeper and deeper waters. Offshore wind is following the same general trajectory, so we're going to see some really interesting concepts for offshore wind, especially when they go to floating wind. And there are lessons to be learned from the offshore oil and gas industry, and many of the people that have expertise in oil and gas are moving into offshore oil and offshore wind. There are important differences, of course, that have to be taken into account. Offshore wind industry is expanding rapidly in several parts of the world. It's not only the US, of course. There are many more projects in Europe. China is investing in a big way, and several other places. So despite all the challenges, I think US is a good example of where you'll see big, rapid growth in this field. So that's all I had to say. I'm happy to answer any questions you should have, or I should say I'm happy to consider any questions you have. I'll answer them if I can. So thanks very much.
Thank you very much, Roger. Such an interesting presentation. I certainly learned a lot. We have a couple of questions already. They keep coming in. Let's start with one about the Jones Act. Do you know if also floating solar parks fall into the Jones Act, or only wind floating parks?
It's not the installation itself that's Jones Act, but if you're supplying equipment to anything floating, I think it will be covered by the Jones Act. So if they follow the same path that they followed for offshore wind, if you supply something to the solar wind panels, for example, so repairs and maintenance, and the ship comes from a US port, that I think will be covered by the Jones Act. Because actually I heard a similar sort of thing in some of the early offshore wind farm work. They were using ships from Canada, and they were saying, "Oh, this doesn't need to be Jones Act." So I don't know if I don't know how feasible that is. But I would suspect, but I don't know for sure. I would suspect that it would be covered by the Jones Act if you're uh, transferring equipment from the U.S. port to the installation that you're servicing.
And a follow-up on that, do you know if there's any other local content requirement besides the Jones Act, for example, on the construction of the turbines, on the material itself?
Well, not so far. I don't think so. It's basically the Jones Act only covers ships. It doesn't cover offshore the installation itself. So the Jones Act was developed for the marine industry. It wasn't developed for the offshore industry.
Mm-hmm.
So it's
Yeah,
the ships that service, even in oil and gas, a crew boat that would go from the Louisiana coast to an offshore installation that would have to be Jones Act.
I remember even there was a problem for one of the hurricanes that some boats were not allowed to transport supplements to these to these islands because they were not covered by the
Oh
Jones
yes,
Act.
yeah. No, I remember that with the Puerto Rico ran into
Yeah,
some kind
exactly.
of problem because they had Hurricane Maria, and then there was another hurricane, and they had to wait for Jones Act ships to supply them, which is a big
Yeah,
issue. Yeah.
true. Another question then. Um, are there any offshore transformer stations under development in the US? Is that part of the infrastructure development?
I just don't know that. I can try and find out. So what kind of installations are we talking about? These are,
I'm not sure. It's a question from Rob Den Rooyen. I hope I did not butcher your name. Sorry. Uh, yeah, offshore transformer stations, maybe like a midway.
oh, I see
Yeah,
for the cables that carry the electricity to shore. I guess that's what they,
I guess so. Yeah.
yeah. Um, I don't know. I could guess. I don't think that's necessarily covered by the Jones Act, but supplying, if you're supplying it from a U.S. port, that would be covered by the Jones Act. It's mainly concerned with shipping rather than equipment, if you know what I mean.
Mm-hmm. Yeah.
For example, I don't think the cable has to be, manufactured in the U.S. It's the cable laying vessel has to be manufactured in
Mm-hmm.
the U.S.
Okay. But the question is more if you know if it is developed or under development, sorry, right now in the US, these offshore transformer stations. If this is part of the infrastructure of the wind parks.
Yeah, I'd have to find out about that. My understanding is that the Jones Act only applies to ships.
Mm,
So I mean, all the wind turbines are going to be not manufactured in the US, I don't think. I mean, not all the
okay.
components, so the generator may be built somewhere else.
All right. A bit more technical question. So about TLPs,
Hmm.
if they are used in areas with risk of earthquakes, is there a serious risk or of fluidization of the ground around the anchors during the earthquakes with risk of losing tension?
I suppose theoretically that's possible, but um, I mean, you can get seismic activity anywhere, but I don't think it's the Gulf of Mexico is regarded as particularly dangerous from that point of view. And TLPs, 95% of them are in the Gulf of Mexico. Um,
Okay.
there's one in the North Sea, and that's not a seismic area. And there's another one somewhere else, which I can't recall where.
So this would be a negative point to install a TLP on the west coast, for example,
Well,
of the US.
well, you'd have to do. They may work very well in seismic zones. I just don't know of any work that's been done to examine that aspect. But yeah, that would be a problem if if you lost your anchoring, then that would be not good
Yeah,
news for a TLP.
no, especially with a TLP.
Yes, exactly.
Yeah. Any, yes, guys. Aha. Well, there is, it's more maybe a comment. Isn't it strange that batteries are included in the source of energy on slide 25?
Yes, I thought that too, and I was hoping no one would notice that because I don't know what the answer to that is. I'd have to look at the where I got that. That's from the Department of Energy, and I didn't have time to figure out what that means. But I have to put that down on something that I have to examine. So someone is paying attention.
Yeah. Um, Considering the size of the floater in floating offshore wind turbines, how likely the floating type is to win over a ground-based solution?
How? Sorry, could you repeat the question, please?
Yeah, so we know that the floater, the floating offshore wind turbine is much larger than the onshore one.
All right.
So how can that one win? How the floating one can win over the shore-based one? I think
Uh,
that's the question.
You mean, I guess, from a technical point of view or from an economic point of
More
view?
on the cost, yeah, more on
Yeah,
the cost of installation.
yeah. I can't answer that because I mean, I did look into how they come up with these costs because there's quite a lot of in North America. There's quite a lot of resistance. People argue on financial grounds that it doesn't make sense to have offshore wind for various reasons. Obviously, it's going to be more expensive in the beginning. Um, So I don't know the answer to that. That you'll have to talk to specialists that look into the costings of these kinds of installations. Um,
And
but I mean, I expect it'll follow the same sort of trajectory. It's the same with oil and gas. You know, I know this for sure with oil and gas is when you first had floating offshore oil and gas, they were more expensive than fixed structures, which makes sense. But
mm,
as they moved further and further out, more and more investment was made in oil and gas structures, and they learnt a lot. Things improved, and I think the installation cost of a floating unit was getting quite close to what they were in fixed structures because of all the refinements. And I expect offshore wind will follow the same trajectory. They're definitely more expensive than what's on land right now. But as they move out into the water and more research is done, more experience is gained, I think that the costs will come down. Whether they'll come down to what they cost on land, I don't know. Because the land has its own issues, they're closer to people and so on.
mm,
And, there's a downside to that as well. But yeah, no, I agree that obviously it's a lot more expensive right now, but I think those costs will come down.
okay. Um, when designing a TLP wind floater, would you prefer, I think that's a personal question, would you prefer to put the buoyancy in the center or above the tendons?
Oh my goodness. Yeah,
If you want, you can have my blackboard.
I'm not going to answer that because I just don't know. Uh, I don't even want to guess what it would be for. Um, I can try and I can talk to people that I know more about this. As I said, I don't have too much direct experience with offshore wind farms, so yeah. Is there some way I can you can get the people's contact information and I can answer some of these questions and get back to people? Because
We
I
can
mean, I
get
could,
the question list. I can get it to you. Yeah.
yes. And then I'll try and answer them, and then I'll get back to you, and you can forward it to uh, whoever wrote the question in the first
Yeah.
place.
I think we still have time for a couple of questions. There's one, I think it's on your area, about the tripod. Which kind of technical challenge are there? On which specific topics an engineer should focus on for these types of installations?
Or you mean the fixed base tripod? Is that what you're talking about? The support for fixed offshore installations, or you?
Let's talk about the floating one then.
Yeah, I
I
thought
think
that's
that's
what
more in vogue now.
yes, yeah. Again, I'm going to stay away from that. You mean a TLP, a tripe with 3 legs rather than 4 legs, or something like that? Is that what they
Yeah, or
mean?
something like that. Yeah. What do you think would be the challenges, the technical challenges for that?
Yeah, I don't think I mean, I can guess, but I'd rather not guess. As I say, I'll ask people who know more about these things. See, this is the danger of talking about things that you're not the expert in. But I told you at the beginning that I was hoping
True,
there'd be more
true.
questions on oil and gas, which is where my experience is. Yeah.
Um, let's see.
Actually, that might be an idea to have another webinar in the future where we can get a person who's expert in floating offshore wind uh, concepts to answer some of these questions.
Yeah, yeah. But we wanted a background first from you.
Yes, yes.
Well, I think we've gone through all the questions from what I can see here. Um, I will, uh, oh, yeah, I, I will then close for now. I thank you very much, Roger, for your such like very, very interesting presentation. I enjoyed it very much. I hope everyone else enjoyed it too.
I enjoyed it too. Thank you.
Uh, Kind Vitesse also thanks you for your time and for your care. And as a token of appreciation, we are offering you a 1-year membership. We'll be in contact with you about that.
Right.
Thank you very much, Thijs Vardenburg. Sorry, I'll be better next time, for the assistance on this webinar. Um, Thank you, everyone, for attending. I hope to see you again next month on March. Hopefully warmer weather here in the Netherlands. I hope you can see my screen now. Next webinar will be March 17th at 7:30. It will be about foldable container solution to global imbalance in shipping. You can, as always, subscribe to it on our page, or of course follow us on our social media, or again sign up for our newsletter. Yeah, that's it. Thank you very much, everyone. Thank you, Roger, for your presentation.
Yeah, thank you for your hosting this. I enjoyed it.
Yeah, have a good evening, guys. Fine
All
avond.
right. Okay, bye.
Bye.